So in my Firestar's family tree video, I said this. You don't really need to do Punnett squares all the time. Punnett squares are mainly for predicting probability, so when you already know what you want the cats to look like, you can just kinda track the lineages of specific alleles and see where they end up, as long as you know how to read the resulting genomes. As I was editing that video, I realized that what I was doing didn't just come from sheer familiarity with genetics. I was using a specific skill in my head, or a kind of an evolution of that skill that I learned in college, and that not everyone has also had the chance to learn that particular skill. It isn't really covered in any introductory genetics videos, or really genetics education videos at all that I've seen around, but when it comes to making genetically accurate family trees for fictional characters, this is far easier and faster, to me at least, than Punnett squares, once you know how to do it. This is not to say that this video doesn't expect you to know how to do a Punnett square. I'm expecting you folks watching to have a basic foundation in genetics, aka, you know basic terms like homozygous and allele, etc., and you can do a Punnett square. If you don't have that foundation already, I have an introductory genetics video linked in the description, but there's 1,000 resources on YouTube and all around the web that can give you one. Learn the basic concepts and then come back to this video. I also have a genetics terminology document that I wrote linked in the description, but that's more of a reminder/supplementary document than a replacement for a real lesson. Anyway, the expectation of this video is that you are a writer, artist, or fan of a fictional piece of media with interest in making a multi-generation family tree with realistic genetics. I'm coming at this from the perspective that we're working with fictional characters, not real-life geneticist stuff. As I've said, Punnett squares are used for predicting probability. They simulate alternate universes where different gametes merge during reproduction, and we can see where some universes are functionally identical. Take this one, for instance. In this scenario, dominant capital A creates a tabby, while homozygous little a cats are solid non-tabbies. If you're a breeder in real life and you want to know the chances of one of your kittens turning out solid, or other scenarios involving real-life uncertainty, Punnett squares are your guy. We can see that with two heterozygous tabby parents, there's a 75% chance of a tabby and a 25% chance of a non-tabby. But if you already know that you want the kitten to be a non-tabby, because this is fiction where you're in control and you get to make that call, it doesn't matter if it's only a 25% chance, it's going to happen. Of course, to adhere to genetic realism, you still need to know that it's possible, but you don't need to keep doing probability equations that you aren't going to use. Plus, Punnett squares are big, they take a while to set up, they only track one generation, it fills an entire notebook in no time just trying to figure out one kid. And again, most of what you're figuring out you aren't going to use. It's a waste of time, space, energy, and math. The method that I'm going to teach you is much more streamlined, simple, visual, and it won't waste any time or math because everything we do is going to be directly useful to us. And it will cover as many generations as we want with just one drawing. It will take longer to set up, but once we have it set up, it's set up for good. Ready? Excited? Let's go. This is a pedigree. You may know it as a family tree, and that is true. It is a type of family tree, but it's a very specific type of family tree. This is not a pedigree. This is also not a pedigree. But this is a pedigree, and so is this, and so is this. Pedigrees are primarily used by geneticists to track specific traits across families, so that they can figure out inheritance models. AKA, we can look at a pedigree to deduce whether the trait we're looking at is recessive, dominant, co- or incomplete dominant, polygenetic, so on and so forth. In order to know how to make a pedigree, you need to know how to read a pedigree. So I'm going to teach you how to read one, and then how to make one. First things first, a circle represents a female with XX chromosomes, and a square represents a male with XY chromosomes. Sadly, pedigrees aren't intersex inclusive, which is a problem. Oh, and do keep in mind that this is just tracking what they can and can't pass on X chromosome-wise, it has nothing to do with gender. Then we have to know what trait is being tracked. For this pedigree, let's say we're tracking tabbies again. A colored-in shape shows us that the tracked trait is expressed. We call this affected. So this colored square is a male tabby. He is affected by the tabby gene. This uncolored square is a male non-tabby. He is unaffected by the tabby gene. It's not doing anything to him because he doesn't have it. Now when I show you this pedigree, you can understand it. Two tabby parents have had a non-tabby kitten. This is just the Punnett square that I showed you earlier, but in pedigree form. If we were looking at real tabby lineages, we would see some that look like this, the one that I'm showing you, and some that look like this. A set of parents who are both tabbies might produce either tabbies or non-tabbies. If the parents weren't tabbies, so they're unaffected by the tabby gene, and they're thus uncolored, we'll see this pedigree. But we'll never, ever, ever see this pedigree. If we were scientists studying the tabby gene, we'd recognize this pattern. We'd see that affected parents can have multiple results, but unaffected parents can only ever produce unaffected kids. We can conclude that the affected phenotype, in this case, tabby, is caused by a dominant gene. See, if the trait is dominant, you can express that trait while carrying another recessive trait, but if you're expressing a recessive trait, that means both of your alleles are recessive, so you can't carry anything different. So if I have, say, 2 solid cats on this family tree, I don't need to write out a whole Punnett square. I can just look at both of them, unaffected, and know, instantly, oh, I can only have solid kittens here. And if they are colored, or if only one of them is colored, again, I don't need to painstakingly draw out a damn square to do this math every single time. I know that individuals expressing a dominant phenotype can carry recessive alleles, and I know, oh, I can make this kitten solid or a tabby, instantly. In real pedigrees, since we're usually using them on unknown genes to figure out if they're dominant or recessive, the quote-unquote affected phenotype, the colored-in one, won't always be the dominant gene. Sometimes we're tracking a recessive gene, so we see colored shapes pop up underneath non-colored shapes, and that's how we realize the gene is recessive. Don't get confused and think that dominant always equals colored. Colored means affected, not dominant. But when we're making pedigrees with already understood genes, we can choose to consistently track what we already know is the dominant gene, just for the sake of avoiding confusion, which is what I'm going to do in this video. So what about co- and incomplete dominance? In cats, ginger is co-dominant, represented by capital O. Homozygous capital O makes a cat ginger, so they're affected by ginger. Homozygous little o makes a cat non-ginger, so they're unaffected by ginger. But heterozygous capital O makes a cat tortoiseshell. They're semi-affected, so we only color in the shape halfway. Here's a pedigree tracking ginger. Unlike 1,000 messy Punnett squares taking up your whole-ass notebook, you can, at a glance, quickly see who's homozygous ginger, who's homozygous not ginger, and who's heterozygous. Ginger is also sex-linked, so it's on the X chromosome. This is why making males and females different shapes is important, so that we know who has 2 X's and who only has 1. For our purposes, as masters of fiction who already know what we want our characters to look like, we can use this semi-colored shape to represent any heterozygosity, including carried genes. Whether the gene be co/incomplete dominant or just plain dominant, whether both alleles be visible on the phenotype or not, the semi-color will henceforth represent all heterozygosity. Real scientists do this too, by the way, just later in the process, when they understand the genes more. This is a pedigree that tracks tabby again, but this time I semi-colored the cats who are carrying the recessive solid allele. Both fully colored and semi-colored shapes are full-on tabbies who look indistinguishable from each other, but the semi-colored shapes also carry a hidden recessive allele. The key here is just to know which traits are dominant versus which are co-dominant, etc., but that's true of Punnett squares too. If you're gonna do genetic stuff, you need to be able to read a genotype, period. If you're working with the A locus, you need to know what A is, what it does, how it inherits, pedigree, or Punnett. It's a good idea to keep a key somewhere on your pedigree to help you remember what you're looking at and how it works. But if you can read this, and know that these cats are tabbies, and this cat isn't, then you can also read this, and know that these cats are tabbies, and this one isn't. One last thing about reading pedigrees. Typically, pedigrees cover more than 2 generations, so just saying parent and offspring can be really confusing. To solve this, we number each generation and put the number in after an F, except for the first one, which is P1. P stands for parent, and F stands for filial. The top generation, the first one, is P1. Second is F1, then F2, then F3, and so on. If that's confusing, then just number them normally. I just want you to know what the F numbers mean in case you see them while you're looking up pedigrees online. So now you know how to read a pedigree, I'm going to show you how I go about making a pedigree. So I have some fictional characters here, and I already know that I want these cats to be tabbies, but I want these 2 guys to be non-tabbies. I have the shapes, and then I have the color layer underneath it. Now, if I want a solid cat, a cat who expresses the recessive phenotype in this case, that means they need to get 1 recessive allele from each parent. Watch how easy this is with a pedigree. Boom. Done. There. Now each of these F1 parents have one recessive allele A that they can pass, but they're still tabbies. They can still pass their tabby alleles onto the sibling, and all the cats still look how I want them to. But in order to carry a recessive allele, the parents need to have gotten it from somewhere themselves. So one P1 parent needs to have given this F1 guy a dominant allele, and the other parent needed to give them a recessive allele. So which parent did they get the recessive allele from? Watch this. Bing, done, easy. I just chose arbitrarily. On this particular pedigree, it doesn't really matter which parent, more on that later. So now I'm gonna type in a recessive little a. Has the side on that, that looks good. Now I'm gonna show you visually what I mean when I say I'm tracking an allele. So this A is this empty white space. It gets turned into a sperm or an egg, and then it gets passed down and becomes this empty white space over here. And then there's also a little a over here with this parent. Yeah, there we go. And then there's these capital A's. So we got this guy's. We got 2 for this person, because it's completely full. And then one of this person's gonna go, right? And then also, you have 1. We can just watch these roll down the waterfall. And then yours is gonna go right there. See, very visual, very simple. Once you get good at reading and making pedigrees through practice, you can start just kind of doing this in your brain. And also that's why it doesn't matter up here which parent here has the recessive. Either way, there's going to be a little a, and it's going to roll down, and it could be either of them. So, hold on, let me delete all these a's. For this F1 cat over here, we don't know any of their parents or siblings or any relatives who aren't descended from them, but we do know that they are homozygous recessive. So there's 2 little a's working here to fully make this space empty. There's no color in here. The other parent got both of these capital A's, or at least 1. We can just bring 1 down, so I'll just... at least 1 A. We might want them to be heterozygous later. It's okay to leave it fully colored while we're unsure. Both the kids here have dominant phenotypes, so we really only just need the 1 dominant allele. So this capital A rolls from the either first generation parent, either this guy or this guy, down to their kiddo, makes them a tabby, and then rolls down to both kids and makes them tabbies. And then, you see, but mom here has nothing but little a's, so she has no color in her circle. So she only has little a's. We're gonna give her 2 of those. So half the circle is clear, half the other circle is clear. That's both them together, making it completely empty. She can only roll down little a's. Whee! So that means both of these kids, both going to be heterozygous. They both have to be carriers. So now our pedigree looks like this. And this is more or less a finished family tree. And about take all of the explaining away, and I could have done that in, 30 seconds? We have a couple of uncertainties. We don't know if this guy is carrying or not. We also don't know if this guy is carrying or not. Personally, I would just write in their genotype, like, A, and then a blank. And this dash here is called a blank, and it means that we don't know. But you could just write, you could also do like a question mark. Whatever works for you. But it's way, 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 way faster, way easier, way less work, and it takes up way less space than like 1,000 Punnett squares would to tell you a bunch of extra stuff that you don't need to know. And not to mention, this is easier to read than 1,000 Punnett squares. And if you're doing this like a computer program, like, with layers, then you can do this. So hide the old layer, make a new one, and then you just only have to draw the same family tree once. And you can do this with as many pedigrees as you want, as many traits as you want. So this is what I was doing in my head when I was making Firestar's family tree. I just had a bunch of pedigrees in my brain, and I was just kind of layering them on top of each other in my brain's mental art program, just kind of mentally rolling various traits down the waterfall and seeing where they ended up, seeing where they could land. Now, this next thing I'm going to teach you is not standard pedigree fare, but we're also not using pedigrees for standard purposes, so that should surprise no one. Pedigrees are really meant to track traits more so than alleles, but we're using them to track alleles. And sometimes, a locus has more than 2 alleles. The bee locus in cats, for example, has black, chocolate, and cinnamon. So the way I'd personally represent this on one of our weird modified pedigrees is just by using different colors to represent different alleles. Here, I'm using black for the black allele, and then for the chocolate allele, I'm using brown, and then for the cinnamon, there's a kind of light reddish brown. So I'm just gonna bring these alleles down to make these kids. Let's see, the first one, I'll bring over mom's black allele, and then I'll also bring over dad's black allele, and she's just black. This next one, let's bring over black allele from mom. And then I probably could have done that on her too. And then we'll bring over dad's cinnamon allele. That'll be fun. And then over here, I want to bring over dad's cinnamon allele again. But I'm also going to bring in mom's chocolate allele. And we have our key reminding us, telling us how to read these genotypes. We see that black is completely dominant over chocolate. That's what this alligator bigger than symbol means. And then we can see chocolate is completely dominant over cinnamon. The co-sign, if you want to do the same thing, this is dominant, and then this is co, and this is for co and complete dominance. I just did that in like 3 seconds, and we can immediately see, because we have this key here to know how to read it, this kid's just black, this kid is also black, and then this kid is chocolate. And I didn't need letters at all. Just very visual, very clear, very easy to keep track of. Just remember that with sex linkage on the X chromosome, the square parent doesn't give any alleles to squares, they only give alleles to circles. In sex distribution, that's the Punnett square that makes offspring into a square or circle in the first place. The square has X and a Y, and the circle has XX. If the kid gets an X from both parents, then they're a circle, and if they get one X and one Y, then they're a square. The sex-linked locus, in this case, the one saying whether a cat is ginger or not, is writing on that X. So if a square parent's giving a Y, they can't also give any ginger-related data whatsoever. Yes, ginger, or no ginger. The kid's just whatever circle parent gives them. Here, let me draw circle parent in. So she's got the 2 non-ginger little O's. So he's just gonna be whatever circle parent gives, in this case, black. But the circle kids get an X from both. Let me put these back. Circle kid gets an X from both. And that can be either X, it doesn't matter. Whee! So their genotype is just the normal 2-letter set, one from either parent. I have a video somewhere on my channel called Calculate Torty Genetics / Offspring Without Punnett Squares. I'll link it in the description. And the technique that I show you in that video works for this kind of pedigree making. Anyway, I hope that helps save you some time and headache next time you have a really big, really complicated family tree to make. Good luck, and bye-bye!